Hello everyone. I'm Ivanna Escala. I'm a Carnegie Princeton Fellow at the Carnegie Observatories, and I'm glad to be joining you today for the Gala Science Meeting to share some of the recent work of my collaborators and I, which are listed here, and include Emily Cunningham, who gave an excellent talk earlier, on making the first chemical abundance measurements in the interstellar halo of M31. Where in this talk, I'll be focusing particularly on its giant stellar stream. So a major focus of our work is linking what we know about M31 to the Milky Way, as learned from spectroscopic surveys such as GALA, to explore broader implications for our understanding of galaxy formation as probed from nearby galaxies. Okay. Oh no. Let me see. My slides are not advancing, so let me just actually manually do it. Sorry about that. So M31 is the only galaxy that we can currently hope to study in a level of detail that's actually comparable to what we have achieved in the Milky Way. So in this way, it can be thought of as a complementary template to the Milky Way. So in order to further motivate studies of M31, I really want to emphasize the sheer scale of this galaxy. So here I have shown an image of M31's optical disk with the moon shown to scale. So its visible disk alone spans a few times the diameter of the moon on the sky. But if we embed this image of M31 in a star count map from the Pan-Andromeda Archaeological Survey, you can get a rough sense of the true extent and also structural complexity of this galaxy. So it provides ample opportunities for detailed studies of its various stellar structures. So in my opinion, M31 is ideal for studies of galaxy formation beyond the Milky Way, because you can see all three stages of this minor merging process represented within its stellar halo. So you have intact satellite galaxies, which are these blue ellipses, that are in the process of falling toward M31 and will ultimately be disrupted in the distant future. But you also have a phased mixed component, the smooth stellar halo, that extends out to at least 175 projected kiloparsecs from the center of M31. And lastly, you have very prominent stellar streams that result from the disruption of galaxies, most notably this large tidal feature labeled E in this image, that is the giant stellar stream. So our primary goal is to constrain the merger history of M31 from its stellar chemical abundances. So what do we know about its merger history? It seems as if it is largely defined by the recent accretion of a relatively massive galaxy. So photometric and spectroscopic studies of M31's disk and halo suggests that it experienced a recent significant disturbance that's consistent with an interaction with the galaxy at least 20% of the pre-merger mass of M31. So this interaction would have occurred within the last 4 gigayears or so. So here I just have shown a plot of some of the data that has led to these types of discoveries, for example, from the panchromatic Hubble Andromeda treasury. So this massive galaxy could potentially be the progenitor of the giant stellar stream, which I've circled here within the star count map of M31. However, recent simulations have shown that you can produce this giant stellar stream feature both in a major merger or minor merger scenario for the formation of M31, although it's only in this major merger scenario that we've thus far been able to reproduce the observed properties of the disk. But the main point is that really the nature of the progenitor of this giant stream is currently unknown. Okay. And I've circled, I guess, the stream within the simulation that's reproduced here. All right, so how does this compare to the Milky Way? So in comparison, the Milky Way's merger history appears relatively quiescent in the sense that it doesn't have this huge disruptive merger that occurs at later times. Its last major accretion event, the Gaia-Enceladus-Sausage merger, occurred about 10 gigayears ago with a stellar mass at infall that's somewhere around 10 to the 8.5 to 9 solar masses. So this event was only hinted at prior to the advent of large astrometric and spectroscopic surveys such as Gaia, Apogee, and now GALA. Where where, as you have seen in earlier talks, Gala data is beginning to be used to investigate the properties of the Gaia-Enceladus merger event and also its progenitor. But anyway, these spectroscopic surveys have enabled the unique kinematical signature of the GS stars to be associated with a chemical signature that is distinct from that of the Milky Way's disk, and also characteristic of a massive dwarf galaxy. So this is the type of thing that we hope to be able to start doing in M31, to use its chemical abundances to untangle M31's assembly history. So we undertook a deep spectroscopic survey of M31 using the DEIMOS instrument on Keck, in which we simultaneously targeted hundreds of stars in each of 11 spectroscopic fields shown here on the star count map of M31, where each rectangle is a DEIMOS field that's approximately a few kpc on the sky. So we measured abundances, meaning the alpha to iron ratio, it's a bulk alpha to iron ratio, and the metallicity for 220 red giant fringe stars. And we did this using both the lower resolution and also slightly higher resolution modes of DEIMOS, and measured the abundances via spectral synthesis. So this yielded the first measurements of the alpha to iron ratio in the outer disk of M31 and the inner halo and the giant stellar stream, which is what I'll be focusing on in this talk, but feel free to let me know if you have questions at the end about some of the other structures. So these 220 stars are a huge expansion compared to the previous state of the art, which was measurements of the alpha to iron ratio for 4 stars in M31 itself. All right, so what have we been able to learn from our chemical abundance measurements in this giant stellar stream feature? So one thing we can do is take the mean metallicity from our data, which is approximately negative 0.8 dex or so, and after some corrections for observational bias, place it on the stellar mass metallicity relation for local blue dwarf galaxies to infer the stellar mass of the progenitor. So we end up finding a value that's about 1 to 5 times 10 to the 9 solar masses. So this work in particular was led by my collaborator, Carolina Gilbert. So this value is between the LMC and M33 in mass, and it's so likely more massive than you would expect for the Gaia-Enceladus merger event. So at face value, again, this is consistent with a minor merger scenario for the formation of the giant stellar stream, but we can't necessarily interpret it that way. So a progenitor this massive accreted relatively late in M31's history is expected to possess a metallicity gradient. And it's unclear where the stars that we're looking at on the sky actually originate from in the progenitor. So one of the next things we did is try to really quantify the presence of abundance gradients within this giant stellar stream feature. So in my most recent paper, we performed a comprehensive study of chemical abundance variations as a function of spatial position on the giant stellar stream, with the aim of providing these constraints for GSS formation models. So here I have shown the metallicity and the alpha to iron ratio as a function of projected radius from the center of M31, where each star is just color-coded by its kinematically based probability that it belongs to this stream feature. So we end up finding a clear gradient in metallicity in the GSS. So it's approximately negative 0.02 dex per kpc. And we don't find any statistically significant alpha to iron gradient, but we're looking at a galaxy that's 780 kpc away. So these spectra are low signal to noise. So we may just not be able to detect a signature in the alpha to iron ratio if it exists.
2 minutes.
Okay. So this gradient is similar in magnitude to what you can infer from, say, the H3 survey for the progenitor of the Gaia-Enceladus merger remnant. However, this galaxy was obviously accreted much earlier at approximately redshift 2. So one thing we need to figure out is how to translate this observed gradient on the sky in the giant stellar stream to the gradient in the progenitor. So that's something that Emily Cunningham and I are working on with a student, Jen Locke at UPenn, using the FIRE simulations to figure out how gradients in dwarf galaxy progenitors translate to actual gradients observed in stellar streams. So that's kind of the next step of this project, is connecting it to the modeling. Okay. So lastly, I'd like to move on to what we can learn from the alpha to iron ratio in M31, although we don't observe a gradient in the alpha to iron ratio as a function of projected radius. So here I have shown the actual relationship between the alpha to iron ratio and metallicity in the giant stellar stream, where the magenta points are what you want to be looking at in this plot. Those are the ones that are most likely to be GSS related tidal debris. And I'm comparing it to the most massive dwarf galaxy around M31, for which we have chemical abundance measurements. Those are the gray points. So one thing that you can clearly see is that the GSS is skewed toward both higher metallicity and also a higher alpha to iron ratio. So there's a lot of scatter in this data and the alpha to iron ratio, and that's just due to the observational uncertainty. So the median value falls around 0.3 to 0.4 dex for the GSS, so alpha enhanced, but it was able to enrich up to metallicities of at least say -0.8 before you start to see some evidence of a decline in the alpha to iron ratio.
I don't think your slide advanced, sorry. We still see the abundance gradient one.
You still see what? Oh crap.
We still see the abundance gradient one.
Okay. That's quite unfortunate. So give me a moment to fix this. I'm using a second desktop. Okay. Okay. Is that any better or no?
No, I see a black screen.
Okay. Technical difficulties. Let me try one more time. Yes or no?
No.
Oh. Oh my God. Okay. Thank you for bearing with me as I try this. I feel like this is kind of inevitable.
Yeah, I mean, over Zoom, there's always some kinks to work out sometimes.
Mm-hmm. Okay. Okay, you know what? I just need to. All right, I think I figured it out. Okay, can you see it now?
No, still a black screen.
Okay, I'm just going to, I literally don't know what is wrong or why it's not working. So I can just verbally finish my talk.
Yes,
and
yeah, go ahead.
I'll answer questions you have, and I'm sorry that you cannot see it. But okay, imagine a plot where you have a high alpha to iron ratio, approximately 0.3 to 0.4 dex in this GSS feature, and it increases, and it reaches metallicities of -0.8, and then begins to show evidence of a decline. So you can imagine comparing this to galaxies like Sagittarius, which actually have a fairly low alpha to iron ratio that's closer to solar, and also things like the Large Magellanic Cloud, and any other relatively massive local group galaxy. And what you'll find is that these abundance trends are obviously distinct. So the point that I was trying to make is that you need to have a high efficiency of star formation in order to get this type of abundance patterns. But something like a dwarf galaxy, even LMC or M33 sized, as far as we know, can't produce those types of patterns. So what the high alpha to iron ratio plus high metallicity is evidence in favor of this merger event having been fairly massive. So that would be a major merger scenario in which the stellar mass was approximately 10 to the 10 solar masses, in contrast to the previous scenario I was discussing, which would be a stellar mass on the order of 10 to the 9. Okay, so that's it.
We have the slide back now, then right as you finish talking.
Okay, fantastic. You can stare at my conclusions.
Can you actually just leave the previous slide up? Yeah.
Can you see this now?
Yes.
Okay, great.
All right.
I hope I painted a detailed picture of it in your mind as I described it to you. So sorry for the technical difficulties. Please let me know if you have any questions.
All right, thank you very much. Do we have questions? So I'll go ahead and start while people think. So this is great work that you're extending kind of galactic archaeology beyond the Milky Way to Andromeda and these other systems. So in this one, it looks like most of the stars are still very high alpha, right? So you only have there's clearly some sort of drop around -0.8 like you had talked about, but the bulk of your sample is still very high alpha, which hints that most of the stars when in this galaxy formed very early, before any type 1a contribution really kicked in. So that kind of seems like a little bit at odds with the fact that perhaps this was a more recent merger. Is there any way to kind of estimate a star formation history for this galaxy based on the abundances?
Well, we do have information for the star formation history of the giant stellar stream from HST data, but that's just for a pencil beam field. So you have to assume that it extends to the stellar populations that are being probed, you know, in our DEIMOS fields. So the giant stellar stream star formation quenched approximately 4 gig years ago from the HST data, although the bulk of its stars have ages around 7 to 8 gig years old, but the populations extend to be as old as 10 or 11 or so giga years old. Regarding the alpha to iron ratio, so I think the high value, you can say that it means that star formation occurred fairly early, but I guess technically, if you see a high alpha to iron ratio, what it means is that star formation was occurring vigorously enough that the contributions from type 1a supernovae were insufficient to deplete the ratio, right? Which is a slightly distinct point, I think. So I tend to think about it in terms of relative timescales between the core collapse and type 1a supernovae instead of early versus late. So I think it's still consistent with a more massive galaxy, especially if most of the star formation did occur like 8 gig years ago and earlier. At least simulations have shown that you can produce these relatively high alpha to iron ratios to high metallicities if you do have things that are on the order of, say, 10 to the 10 solar masses or so. Does that answer your question?
Yeah. Do we have any other questions?